Hello everyone, and welcome to this chapter 32 of your book. This will be the last chapter of our sections in which we studied threads. So we'll be concluding this concurrency related section in this chapter. And this chapter is about basically the common mistakes that people make when doing multi-threaded programming. Okay, so the common bugs that arise and how you can prevent those bugs. Okay, so this will be our topic of this chapter. So let us start. So when you are programming using multi-threading, there can be two kinds of bugs. One, multi-threading, this concurrency and multi-threading basically is the same thing. So concurrency related bugs, they can be classified into two different categories. One are non-deadlock bugs and the other is deadlock bugs. So deadlock, as we have slightly seen in the last chapter, that deadlock is a situation in which you have multiple threads, they are waiting for each other and none of them is basically able to make progress. Okay, since none of them is being able to make progress, so none of them basically releases the resources that the other is waiting for. Okay, so this way there is a circular wait condition in which everybody is waiting for the other thread to release a resource before it can release its own resource, and the other thread is waiting for the original thread to release its resource before it can release its own resource. So this way there's a circular dependency and everybody is waiting for each other and they're all stuck. None of them can make progress. So we saw this in most recently in the last chapter when we studied the dining philosopher's problem. So we'll study it here again, deadlock and bugs related to deadlocks. But in the first part of this section, chapter, we basically start with bugs that are not related to deadlock. Okay, so non-deadlock bugs. So non-deadlock bugs basically essentially are programming errors which happen because we have not taken into the multi-threaded nature of our program into consideration. Okay, one of the most serious consequences of having a multi-threaded program is that the scheduling of those threads is not in our control. Okay, and the scheduler can schedule any thread anytime. So if we don't keep this thing in mind, then uh, we can have some bugs in our program which will happen because they rely on assumptions which were true in a single threaded program but which are no longer true in a multi-threaded program. So let us see how we can detect and deal with these non-deadlock bugs. So the first non-deadlock bugs is atomicity violation. Okay, so let's see what is atomicity violation, how atomicity is being violated. So in this thread, we are checking the value of this proc info. Let's say this proc info, it's a pointer. So if we're checking if this pointer is not null, then we go into the if body and use this pointer. Okay. So if thread underscore proc info, basically if the value of proc info is null, null evaluates to false in if conditions. So this condition will become false and we will skip this if body and do not use this pointer, okay, which is a correct behavior. So when we are inside this if, then we are sure that uh, the thread underscore proc info pointer is not null, okay, because this will be true only if this pointer is not null. Okay, so if the pointer is null, then this condition will evaluate to false and we will skip the if body. Now this assumption that if we are inside the if body, then thread underscore proc info must be not null. Okay, so this is clear from looking at this code. But this assumption holds only if our thread our program is a single thread program. In multi-thread program, even though it looks true that if we are in the if body, then thread arrow proc info must be not null, even though if it looks true, but it can happen that this might not be the case. How? Because let's say there's another thread in which we are making proc info equal to null. Okay, and since scheduling is not in our control, then it might very well happen that thread 1 is scheduled and at that time thread underscore proc info is not null. Okay, so thread 1 is scheduled, it checks the value of thread arrow proc info. It is not null. It goes inside the if body. And before it reaches here, line number 4, there's a context switch. On line number 3, there's a context switch. And thread 1 is descheduled and thread 2 is scheduled. Okay. Thread 2 runs and it makes proc underscore info equals null. Okay. Now, since this is the same proc underscore arrow proc underscore info, which is being globally shared between these two threads, and this thread 2 has made this pointer equals to null, then when thread 2 is rescheduled and thread 1 is scheduled again, then even though we are here on line number 3 inside the if body, and it appears that here thread arrow proc underscore info can never be null, but still we have seen that due to this arbitrary scheduling, when thread 1 checked the value of proc underscore info, it was not null. Therefore, it went inside the body loop. But by the time it arrived on line number 4, thread arrow proc underscore info was made null by thread number 2. Okay, so when this function uses this pointer here, thread arrow proc underscore info, it assumes that this value is not null, but since actually this value is null, then this function will try to use a null pointer and this program will crash. Okay, so all this just because our assumption that if we are inside the body of if loop, then thread arrow proc underscore info must not be null. Okay, and which is true in a single thread program. Okay, because we have made sure before going into the if body that it is really not null before we use it. Okay. So, but this assumption, as we just saw, does not hold in the multi-threaded case. So, we should always keep in mind that scheduling is not in our control and threads can be scheduled in any arbitrary order. Therefore, we have to take precautions ourselves to make sure that when we use this thread arrow proc underscore info, it is really not null and we should not rely on the scheduler. So here is an implementation in which we control access to this thread arrow proc underscore info using this lock. Okay. So this access to this pointer is controlled by this lock in this thread 1, and the same access to this pointer is controlled by the same lock in thread number 2. Okay. Since this lock is global and shared between these two threads, and from the behavior of locks, we know that only one thread can acquire a lock at any given time. Therefore, if thread 1 has acquired the lock, it has checked that pointer is not null and it has gone inside the if body. Let's say at line number 6, there's a context switch and thread 2 runs. Before making the pointer null, it will try to acquire the lock. Okay? And since lock behavior guarantees us that thread 2 cannot acquire the lock while thread 1 is holding it, remember thread 1 has not released the lock yet, it is still holding this lock. So therefore, thread 2 cannot make the pointer null. It will block here and go to sleep. Okay? So eventually thread 1 will be scheduled, it will complete its task and release the lock, and only after that thread 2 will be able to acquire the lock and make the pointer null. Okay, so thread 2 was unable to make the pointer null during all this time that thread 1 had the lock and it was using this pointer. So as I said, we cannot rely on the scheduler to guarantee this condition of atomicity. Atomicity basically is here that this section is executed in an atomic fashion. Okay, it cannot be interrupted in the middle and some other code executed in the middle of this section which manipulates proc info. So by using locks, we made sure that this portion of the code 9.5 to 9 is executed atomically and mutually exclusively. Okay, so this is how we can tackle this kind of bug. This is one non-deadlock bug. Secondly, the previous bug related to atomicity violation, and here we have this second bug which relates to order violation. Okay. Sometimes we assume an order in the execution of our threads, which should not be assumed at all because scheduling is never in our control. Okay. So let's see what happens here. So you have thread 1 which creates a thread of this main function, another thread. This thread 1 is already running and it creates another thread of this m main function and returns some pointer to be stored in m underscore thread. And in the m main function that will be created by this thread, we are using this pointer that has been returned by this function creation during the creation of m main thread. Okay, so implicitly it is assumed that since thread 1 is creating the main function, creating the thread of this main function, the m main function, this m main function will not be able to execute before this function has executed and assigned the value to m thread. Okay, so the problem is here there are two steps happening. This thread is being created, m main, and as a second step, the value returned by this function is being assigned to m thread. Okay, so it might very well happen that the first step is completed, a main thread is created, and before we can assign the value to m thread, thread 1 gets descheduled. Okay, so thread 1, m thread will have its own original value. Let's say it was null. So m main thread has been created. So thread 1 gets descheduled and this thread 2 gets scheduled. So thread 2 is basically its m main function. It tries to use this m thread function pointer. Okay, now since the value in m thread has not been assigned yet and it is still the old value which might very well be null, so here we are using, it is possible that we use a null pointer here. Okay, and null pointer, using null pointer here will crash our program. Okay, so all this because we had assumed that m main will always be executed after this line has assigned the value to m thread. Okay. Now this assumption is not true because this creation of thread and assignment of value to m thread are two separate things, and since scheduling is not in our control, then it might very well happen that a main thread is created and before the assignment of value to this pointer m thread, thread 1 gets descheduled. Okay, and meanwhile m main thread gets scheduled and tries to use this m thread state. Again, we relied on this implicit order which is not at all guaranteed by the scheduler. So if we want to make sure that m main executes after value has been assigned to m thread, then we have to make sure of it ourselves. Okay, and we exactly have these kind of structures provided by the operating system in which we can make a thread wait until a certain condition becomes true. Okay, so we can always put such a structure, the condition variable in m main, that it waits until value has been assigned to m thread before it can go ahead and use this pointer. Okay. So here we have this implementation using condition variable and associated lock, and this in a minute pointer, a minute value equal to 0, which basically tells you that whether m thread has been initialized or not. So here you see that when we create this thread m main and assign the value to m thread, only after that we make m init equal to 1 and conditional and signal this condition variable. Okay, the main thread, if it runs before value has been assigned to m thread, it will basically check that m init is not 0. M init is not 0, which means m thread has not been initialized yet. Okay, sorry, m init is 0, which means m thread has not been initialized yet. So it will basically wait for this condition variable. Okay, it will go to sleep and wait for this condition variable before it can use m thread. Okay, so it goes to sleep and eventually wherever this thread was, thread 1, it will be scheduled and value will be assigned to m thread, and it will make init equal 0 and condition this signal variable, and only then m main thread, which was waiting on this condition variable, will wake up, check that m init now is equal to 1, get out of this loop and use this thread m thread variable. So here we have basically guaranteed this order that m main executes after value has been assigned to m thread ourselves. Okay, so we ourselves have put in locks and condition variable to make sure that this line in M main does not execute before value has been assigned to M thread. So this is again a bug which is not a deadlock bug, but still it happens in multi-threaded code because we assume a certain order in execution of our threads. Okay, and that order is violated by the scheduler because scheduler is not in our control. It can do anything it likes. So now let's come back to the second category of bugs, which we call deadlock bugs. Okay? So what is a deadlock? A deadlock, as we have already discussed, is a condition in which threads are waiting in a circular wait. They are waiting for each other to release their resources so that they can go ahead and acquire those resources and do their task or make some progress. Okay, but the thing is, the wait is circular. Since the wait is circular, then everybody is waiting for everybody else, and in that case, no progress can be made. So since no progress can be made, then we call it a deadlock bug. So this is one of the simplest examples of a deadlock involving two threads. So here we have two threads, thread 1 and thread 2, and basically these threads are acquiring these two locks L1 and L2 before they go ahead and do some work. So let's see. Thread 1 basically first acquires L1 and then acquires L2 and then goes on to do some work. Thread 2 first acquires L2 and then it acquires L1 and then it goes ahead. Once it has acquired both the locks, it will go ahead and do some work. So it might happen that scheduler can schedule them in any way. So one of the ways in which it can schedule these two threads is that thread 1 is scheduled, it acquires L1, and before it can acquire L2, it gets descheduled. Okay, so thread 1 basically acquires L1 and gets descheduled. Thread 2 gets scheduled, it acquires L2 and it tries to acquire L1. Since L1 is being held by thread 1, this will block here in the wait of L1. Thread 2 has acquired L2 and will block in the wait of L1. So since it is blocked, it will be descheduled and thread 1 will be scheduled again. It had descheduled here after this acquiring L1, so it will try to acquire L2. And since it will try to acquire L2, L2 is being held by thread 2, so it will block here. Okay. So thread 1 is blocked waiting for the release of L2, which is being held by thread 2, and thread 2 has locked waiting for the release of L1, which is being held by thread 1. Okay. So they both are waiting for each other to release their resources, but nobody can move forward because thread 2 is waiting for L1, which is being held by thread 1, and thread 1 is waiting for L2, which is being held by L2. Okay, so this way they both are waiting for each other to release their resources, and they are both asleep and nobody is being able to make any progress. So this kind of bug in our programs, we call it a deadlock bug. Okay. So why do deadlocks occur? There are some conditions that need to happen when in our program there is a deadlock. Okay. So here, as we just discussed, there is this circular dependency. Thread 1 holds lock 1 and is waiting for lock 2. Okay. Thread 2 is holding lock 2 and is waiting for lock 1. Okay. So there is this circular dependency. Okay. So thread 2 holds lock 2, which is wanted by thread 1. Thread 1 holds lock 1, which is wanted by thread 2. And this circular dependency, you can continue it like this, and basically they will be keeping waiting for ever. So the conditions, so circular wait is only one of the conditions that need to happen for deadlocks to occur. So we'll see later how we can basically what kind of conditions need to happen and how we can prevent the occurring of deadlocks in our program. Encapsulation, hope you have studied this in your OOP course. So encapsulation basically hides a lot of details from the user. So encapsulation also, hiding the details basically poses a lot of problems. Let's say you have those two vectors, vec1 and vec2, and there's a function called v1.addAll v2, okay, which basically will add all the elements of v2 to the elements of v1. So let's say one thread calls this function, and since we don't see anything here, internally assume that this function needs exclusive access to v1 and v2 before it can add the elements of these two vectors. So internally it uses two locks to acquire access to v1, exclusive access to v1 and exclusive access to v2. So lock associated, it first acquires the lock associated with v1 and then acquires locks associated with v2. Only then it goes ahead and adds the element of these two vectors. So let's say one thread calls this function, and at the same time another thread calls this function. Okay, so it is basically the same operation but in reverse order. Here v2.addAll, it will add all the elements of v1 to v2. So since these two functions are being called in two different threads, and here this function is being called for v2, so it will acquire the locks in the reverse order. It will basically acquire first the lock for v2 and then the lock for v1, and then go ahead and add all those elements. So since these two functions are being called in two different threads, they can be executed in any order at any point. Any thread can be rescheduled, etc. So this will exactly create this problem here that we discussed, that first they acquire a lock to v1 and then to v2, and here the thread 2 acquires first lock to v2 and then to v1. So it might happen that here we have a deadlock, okay? And the user will never know that there is a deadlock because all the details, what happens when add the elements, they are hidden in the inside the function. Okay, so as I said, there are certain conditions for a deadlock to occur. This condition must be present when there is a possibility of a deadlock. So these conditions are mutual exclusion. So first of all, these threads are accessing the resource in a mutually exclusive way. Okay? If the threads are not accessing the resource in a mutually exclusive way, then they do not need to use locks, and since they do not need to use locks, then there is no question of deadlock. Okay, so first of all, threads must be using locks and trying to access the resource in a mutually exclusive way for a deadlock to occur. Okay. Secondly, each thread is accessing more than one locks. Okay, so it is basically holding one lock and waiting for another. So there is this hold and wait condition which needs to happen if the deadlock is to occur. Okay, so again, hold and wait means we are using more than one locks, and one thread is holding one lock and waiting for another. Secondly, there is no preemption. Let's say a circular wait has been established and a deadlock has occurred. Preemption means there must be some way to break this circular wait. Okay, or a thread, if it realizes that it's in a deadlock, it should release all the locks that it is holding. Okay, so it should preempt and throw away all the locks that it's already holding. So again, since there is no preemption, no thread is releasing the locks that it is already holding, then a deadlock will continue. Okay, so preemption may be a means to avoid this deadlock condition. So we'll see how we can preempt. And secondly, a circular wait has to happen for a deadlock to occur. Okay, so it might happen that multiple threads are holding and waiting for different locks, but there is not a circular wait. In that case, it's not a deadlock, and eventually some thread will make progress. Okay, so for circular wait, for deadlock to occur, the wait must be circular. Okay, so it might be between two threads or it might be between more than two threads. So let's see how we can prevent these conditions from occurring so that we can avoid deadlock. Okay. So circular wait can be avoided by imposing an order in our program or threads when they acquire locks. Okay. So remember in our example here, the threads were acquiring locks in reverse order. Okay. So if we pose an order that every thread, if it wants to acquire these two locks L1, L2, it should always acquire it in the same order. I mean, every thread should proceed acquiring the locks in the same order, first L1, then L2, or first L2, then L1, then the circular wait can be avoided. Okay. Secondly, there is this hold and wait condition. So basically we are holding some resources and we are waiting for other resources. Okay, so basically if we are trying to acquire multiple locks, then we have done half the work. We have acquired some locks and we are holding them, and we have not done half the work, which means we are some locks we are not able to acquire and we are waiting for those other locks. Okay, so this again hold and wait condition, where we have done acquired half the locks and waiting for the other half, this can be avoided if we perform this acquisition of locks atomically. Okay, so atomically means if we have to acquire L1, L2, then this acquisition of locks should be protected by another lock. Okay, and basically any thread which wants to acquire these locks must first acquire this lock, prevention lock, before it can go ahead and acquire these other locks. Okay, so prevention lock will basically prevent multiple threads accessing these resources at any given time, these locks at any given time, and only one thread will be able to acquire the prevention lock and acquire all these resources. So this way we are making sure that while we have acquired L1 and we are going to acquire L2, basically no other thread can come and acquire L2 before us, because that thread also will have to first acquire the prevention lock which we are holding, so that thread will not be able to acquire the prevention lock, so it will not be able to enter this section and acquire L2. Okay, so this acquisition of locks is happening atomically. We are basically either acquiring all the locks or we will be blocked at here and we will acquire no lock. So there won't be a condition where we have acquired half the locks and waiting for the other locks. But this should be implemented in all the threads, that all the threads follow this protocol if you want to access these locks atomically. So this is another way of protecting or preventing deadlocks. Secondly, as I just said, there was no prevention in our code, in which case basically a thread that is holding some resources will continue holding them. Okay, prevention means if the thread realizes that there is a problem, then it should release the resources that it is already holding, so that those resources can be given to another thread which is waiting for them. So basically simple preemption mechanism can be implemented, that a thread tries to acquire locks one by one, and if the acquisition of some lock become unsuccessful, it should basically release whatever it has already acquired, okay, and try again. So here it is like thread acquires this lock L1 and then it tries to acquire L2. Okay, so try lock is another function which will try to acquire a lock, and if it fails, instead of sleeping, it will return, okay, with an error. So it acquires L1 and tries to acquire L2. So if it sees that it has there was an error and it was unable to acquire L2, then instead of holding on to L1 which is already acquired, it should also release L1. Okay, so it should release all the resources that it has and go to try again. Okay, so this way, since it has released L1, then if another thread was waiting for L1, that thread will get L1 and it will be able to make progress. Okay, so we'll avoid a deadlock. So this is a preemption mechanism in which a thread basically releases all the resources that it has already it is already holding if it detects that there was a problem in acquiring further resources. Okay, so this is also a method to prevent deadlocks and break circular wait so that some thread can make progress. There are also other mechanisms to prevent deadlock, which is basically mutual exclusion, in which the threads that are trying to access the shared resource in a mutually exclusive manner, they are using locks to implement mutual exclusivity. Okay, so in some cases, it is possible to have exclusive access to a shared resource without using locks. Okay, so how do we do this? This can be done using atomic instructions. So we know there are some atomic instructions that are available to us in the computer or the processor ISA, instruction set architecture, okay, in assembly language. So we had already discussed this compare and swap instruction, which basically takes an address, compares this value, old value to the new value, and if the old value is equal to the expected value, it will replace this with the new value. Okay. So this instruction can be used to do atomic increment. Remember, we had this problem with counter is equal to counter plus 1 in multi-threaded code. That was because counter is equal to counter plus 1 was 3 instruction in assembly, and threads can be scheduled at any point, so it was causing a problem. So this increment operation on a shared value, we can do it in this compare and swap instruction. Okay. So compare and swap instruction, we give it the pointer, the address of the value, and then we give it the old value, and here let's say we give it the new value. In our case, it should be old plus 1. Okay. So it will check this value, old value is equal to the value at this address is equal to the old value, and if it is true, it will replace the value at this address with the new value, which will be old plus 1. Okay, so the value will be incremented by 1, and this operation will happen atomically. Okay, so there is no chance that any thread can interrupt this operation in the middle, and we will have a wrong value of the counter. Okay, so here we are using this counter is equal to counter plus 1 operation, but without locks. Okay, so mutual exclusion in some cases can also be obtained by using atomic instructions. So this is one example. Again, a second example of this same using atomic instructions to achieve mutual exclusion is this code where we are inserting an element in the linked list. Okay. So we have to basically check this value that the head node is not null, and this assign this value to new node. So this will be a new node that is created, and we want to insert this in the linked list. Okay. So we want to insert it from the head side. So we basically point this nodes next to the old head, and then we replace head to this node. Okay, so this operation is happening in 2 steps, and if a thread gets descheduled between these 2 lines and another thread comes and changes the value of head, then basically we have lost the this linked list will be corrupted. So either we basically make this operation atomic by using locks, just like here, okay, as we would do normally. So we can make this thing atomic, or we can use an atomic instruction to make this swap of next and head. So here basically we exchange the value of head with this new node using this atomic instruction. Okay, so by using this instruction, we basically do not need locks. So this is another example where use of locks can be avoided using atomic instructions. Okay, and since when we are using atomic instructions, we are not using locks, so there is no question of having a deadlock. Okay, this is another way where in some cases we can avoid deadlocks in our programs. So again, deadlock avoidance via scheduling also is a technique which is possible only if your scheduler is intelligent enough and is like it has enough knowledge about the threads. So let's say we have 4 threads and 2 locks. So this table gives you which thread is using which lock. Okay. So here we can see that T1 and T2, they both are using L1 and L2. Okay, so and the other threads are not using both the locks. T1 is only T3 is using only one lock, and T4 is using no lock at all. So if your scheduler can in some way detect this information, then it can guess that if a deadlock has to happen, it can only happen between T1 and T2. Okay. So what it can do is that it can, when scheduling those threads, it should try that T1 and T2 are never scheduled at the same time. Okay. So if T1 and T2 are never scheduled at the same time, then they will not be able to interfere with each other, and they will not be able to steal resources from each other and cause a deadlock. Okay. So here, as you can see, T2 is always scheduled on the same processor as T1 and after T1, okay, which means T2 will be acquiring its lock only after T1 has acquired and released its lock. Okay. So there will be no chance of them doing a hold and wait and resulting in a circular wait. Okay, so this is also uh, like a way in which deadlock can be prevented, but it's only possible in limited systems because usually scheduler has no knowledge about threads. So detect and recover is another strategy which is used in databases to detect that deadlock has occurred. So basically, if there are certain group of threads which are making no progress at all for a very long time, then the database server will detect that if they are waiting in a circular loop waiting for each other, then it will conclude that there is a deadlock, and what it will do is it will try to recover from the situation by, for example, let's say killing a few threads or few programs. So killing a thread basically would release all the resources that it is holding, and they will be given to whoever thread was waiting for that particular resource, and then that particular thread can make progress. And this thread which has been just been killed, it can be restarted to do whatever it was supposed to do later. Okay, so this is another strategy that is used in some database servers, detect and recover. So these were basically some of the problems or errors or bugs that can occur in our code if we are using multi-threaded programming. Okay, so some of them were non-deadlock bugs and some of them are deadlock bugs. So now I hope this gives you a good idea of what kind of problems you can have in your multi-threaded code and how you can avoid those problems. Okay, so remember, one thing you have to consider is that uh, scheduling is not in our control, so we cannot assume any assumptions that were true in the single threaded case about atomicity of a code or about ordering of a code. Okay, so we cannot assume any assumptions. If we want to assume about atomicity or about order, we have to explicitly ensure that assumption of atomicity or order in our own code using locks and condition variables. Okay, only then we can really say that our atomicity is not being violated or the order is ensured. Okay. Otherwise, we cannot assume anything because scheduling is not in our control. Secondly, there is always a possibility of deadlock. So again, we studied different conditions under which deadlocks occur and different situations where uh, we can avoid those conditions and avoid the production of deadlocks in our code. Okay. So hopefully this will help you when you write multi-threaded code. So I'll end it here, and if you have any questions, you can come and ask in the synchronous session. Thank you very much.